give a very warm welcome to Zach!
I do. Hello. Good evening. My name is Zach, and I'm going to talk to you about microfluidics and why ultimately making things smaller is better for everybody. But before we get into it, I've got some questions. So first of all, I want you to give us a cheer. Who in the room has used a pregnancy test? A few of you, right? Who in the room has used an inkjet printer? Yeah, almost everyone. And I would be very surprised if there is a single person in this room who has not used a lateral flow test. You've all used them, right? So what do these three things have in common? They are all, in fact, microfluidic devices. Now, microfluidics is the field that I work in, and I've been working in it for 8 years. And what does it mean? So let's break it down. Micro means small, and fluids are liquids and gases. I exclusively work with liquids, so that's what I'm going to be focusing on this evening. And I was first told an analogy by my boss ages ago, like 8 years ago, where he said, stuff at the microscale doesn't behave as you might expect it to. So, like, weird and wonderful things happen. So imagine you've got a channel that's like Y-shaped. So there's an inlet, two inlets, and then a straight channel, and then two outlets. Is that me doing that? Is there a dinosaur loose? Great. So we've got this Y-shaped channel that goes in, the straight bit out. And I was told if you put in like red paint and blue paint, they mix, and you get purple paint out of both outlets, because that's sort of what we're used to. We're used to a turbulent world where stuff mixes. But if you do the same thing at the microscale, you can put in red paint and blue paint and get out red paint and blue paint. And I had no reason to doubt my boss. He was like telling me that this is how it works. And I thought, yeah, all right. And then I thought, you know what? I'm going to give a talk about this. I should bring receipts. I should check that it works. So I 3D printed this pipe. And you can see that I've got water with red food colouring in it and water with blue food colouring in it. And if this video plays, cool, you can see that we have red going in and blue going in, and we get sort of a reddish purple out of both outlets. And I hope this isn't a surprise to anybody, because this is what you would expect to happen. I will admit that the red was quite a lot stronger than the blue, so it is not very purple, but they mixed. Now, I did the exact same experiment, but I shrunk it down. And when I say I shrunk it down, I made a chip, which is in here. And I did the same thing at this scale. And I've got an image of it here. So, hopefully you can see, I know it's a bit faint, I'll come over here, that there is going in, and blue water going in, and red comes out, and blue comes out. There's no mixing via turbulence. The only mixing happens by diffusion, which by comparison is a very slow process. So what's the difference between these two experiments? The only difference is scale. Now, my 3D printed pipe is about 15 millimeters in diameter, and the device on the right is 128 microns in diameter. Now, a micron is a millionth of a meter. Compared to the qubits that they were talking about earlier, my devices are massive, but for what we're used to, they're really small. You might have heard the fact that human hair is about 100 microns in diameter. I'm not follically challenged, but I do have a beard. So I plucked one of my beard hairs and I put it under the microscope, and this is one of my beard hairs with that channel. So just to reiterate, the channel is 128 microns wide, and the diameter of one of my beard hairs is 133 microns. So you can think of the devices that I make, I'm like a tiny plumber whose pipes are the size of hairs. So that's what I do, that's microfluidics for you. And it's not only tiny length scales I deal with, I also deal with tiny volumes of liquid. So hopefully, on all the tables in front of you, there'll be a pint of water. What I'm going to invite you to do is just dip your finger in the water and look at the drop that's on the end of your finger. So, that droplet that's on the end of your finger is about the size of a grape. It's about 50 microliters in volume. You can get rid of that now, by the way. The droplets that I work with are between 100,000 and 100 million times smaller than that. So really, really small. If you didn't know, metric prefixes increase every time something gets 1,000 times bigger or smaller. So starting with a litre, 1,000th of a litre is a milliliter, and 1,000th of that is a microliter, and then it goes nanoliter, picoliter, femtoliter, and attoliter. So 50 microliters is up here, and I work in picoliters, femtoliters, and attoliters. Now, on the table in front of you are also two vials, one with a white lid and one with a blue lid. What I want someone to do on your table, or like two of you, is take the vials. I have some of my own. And what we're going to do is we're going to shake them. But we're only going to shake them for 5 seconds, okay? And it's important that you're going to shake them, and then you're going to put them down, and please don't touch them. I know it's really tempting to fiddle, but just leave them be, okay? So is everyone holding the vials? Yeah. Cool, so we're going to shake for 1, 2, 3, 4, 5. Great. Now put them down and leave them be. We will revisit these later on in the talk. What's in these vials, you may ask? So both of them contain water. It's got blue food colouring in, just to make it look a bit prettier. The one on the left, the white one, contains sunflower oil. And the one on the right contains sunflower oil and a surfactant. Now, the surfactants are also called emulsifiers. What you have basically done just now is created an emulsion. And an emulsion is a dispersion of one liquid inside another liquid. So you should be able to see that there are tiny little drops of oil now floating on top of the water. And the reason that we use surfactants, and the reason that surfactants are so important in the work that I do, is that they can stabilize the emulsion. It's like the difference between balsamic vinaigrette and mayonnaise. So balsamic vinaigrette is olive oil, balsamic vinegar, right? You shake it up, you make your dressing, you eat your salad, everything's great. But if you make it an hour ahead of time, by the time you come to pour it on your salad, it will separate back out again. And that's because it's an unstable emulsion. However, you can take the same ingredients of oil and an acid like lemon juice or balsamic vinegar and add egg yolk to it. An egg yolk contains a group of proteins called lecithin, and if you shake that up, you make mayonnaise. And mayonnaise is an incredibly stable emulsion. I think a jar of mayonnaise would outlast everybody in this room if you were to wait for it to separate. Like, it's never going to separate back out into oil and water. So what does a surfactant look like? This is sort of just a basic analogy. There's it's got a head group and two tails for most surfactants. And the head group really likes water, and the tails really like oil, and they will align themselves on the interface between the two liquids and stabilize the droplets. And this means that you can treat each droplet like its own test tube, and that is where the power of droplet microfluidics lies. So if you had two droplets, when they come together and touch each other, they bounce off each other. They don't coalesce into a bigger droplet. And we can do things with this, and that's what my PhD has been focusing on. So in this video, I've got a demonstration of how droplets are being made. So from the left, we have water and some polystyrene beads. We use beads because cells are finicky and just a nightmare to work with, so I like beads because I can't kill them. And then we have oil coming from the top and the bottom. So when this plays, you can see that it pinches off individual droplets, and most of the droplets contain a single cell. So this is really useful, but it's quite a slow process. An alternative way of making droplets is by shaking, like we did just now. But one of the problems when you make droplets by shaking is that they're all different sizes. So part of my work during my PhD was on this device. Here we have a mixture of emulsions coming in from the left, two sheath flows which focus it, and then two outlets. The top one is for the light coloured droplets and the bottom one is for the dark coloured droplets. And as you can see, as this goes, what you can't see in this video is there's actually a laser pretty much where the mouse is, actually. And the laser is detecting the light coloured droplets, and then they're being sorted into the different channels. And this device was created because most of the ways that you want to manipulate droplets rely on them all being the same size. But as I mentioned before, it can be really frustrating to rely on making them on chip because it's slow. So if you could make them quickly, you could then do your experiments faster. And most of the work that I do is about making things smaller in order to make them faster, more efficient, and basically cost less. So, this is another device I made, and I wanted to include this in my talk because it didn't work. And I think it is important to showcase that sometimes when you do research, stuff does not work. So, these droplets were all meant to be the same size, and they clearly are not. But one of the reasons I included it is a great example of the fact that when the droplets are close together, they bounce off each other and they don't merge. I made this device because the technological barrier for entry of microfluidics is about 10 to 15,000 pounds. That's the minimum spend you need to buy the equipment necessary to start working microfluidics. However, some of the devices I use, I work in the clean room at the JWNC, cost sort of £200,000–300,000. This device has got 2 layers and ordinarily would have taken a £170,000 mask aligner to make. I did it with my £10,000 worth of equipment. So I've been trying to lower the technological barrier of entry to make microfluidics more accessible. And that's important because of how useful microfluidics is. So, why? Why am I telling you all of this? What can you do with microfluidics? I'm being sponsored by the company I used to work for, and they used to sell an instrument that they would sell to big pharmaceutical companies for screening drugs. And the way that a conventional drug screen would work is that you would plate out cells into these microtiter plates. You would do an experiment on them. It would usually involve color changing. You'd watch to see like, oh, this one changed color, so this is good, and I want to keep that cell. To process 1 million cells, you'd need about 30,000 of those plastic plates, which would probably fill the vast majority of this room. Each cell requires an amount of reagent, so let's say it's a milliliter per cell. That's 1,000 liters of reagent required for this screen. It also takes a very long time to process those cells. Even if you're using liquid handling robots and very expensive automation, it probably takes you about 3 months to process 1 million cells. But if you encapsulate cells in droplets, like I showed before, you can fit 1 million cells in droplets in a teaspoon. And you can process those 1 million cells in a day. So droplet microfluidics is all about increasing throughput, making things faster, smaller, more efficient. So we'll go back to the files. This is a video that I recorded, and this is sped up. So hopefully what you can see is the droplets on the left are all coalescing, and they're all merging. And by the end of today, they'll have separated back out into the oil and water layers. But the vial on the right has created a stable emulsion. And when I first tested this 2 weeks ago, I still have a vial of this emulsion, and it has remained stable for 2 weeks. So it's not quite mayonnaise, but it's pretty good. Anyway, this has been a little journey into microfluidics. Thank you very much for listening.